How to solve DC-DC converter stability issues. If you are facing stability issues with your direct current to direct current converter, you are not alone. Many engineers encounter similar challenges. Let's break down how to tackle these problems effectively. First, it is essential to understand that the stability of a direct current to direct current converter largely hinges on the control loop. This loop is responsible for regulating the output voltage or current by adjusting the switching elements. When this loop becomes unstable, you may notice oscillations or an inability to maintain proper regulation. One of the first steps to address stability issues is to focus on control loop compensation. This involves designing the feedback control loop with the right compensation to ensure you have adequate phase margin and gain margin. Analyzing the loop gain and phase using Bode plots can help you adjust compensator components like error amplifiers and compensating networks to avoid unwanted oscillations. Next, consider the importance of input and output filtering. Filters play a vital role in reducing noise and preventing oscillations caused by resonances. However, be cautious with input filters, especially LC or PI-type filters, as they can introduce additional poles and zeros in the control loop. To mitigate this, adding damping elements such as resistors or using capacitors with appropriate equivalent series resistance can help smooth the frequency response and maintain stability. Component selection is another critical factor. When choosing inductors and capacitors, ensure that inductors have the correct inductance value and are made from materials that do not saturate under operating currents. Saturation can lead to nonlinear behavior and instability. Capacitors should have suitable voltage ratings and low equivalent series resistance values to ensure stable filtering and a good transient response. Implementing a soft start function is also beneficial. This function allows for a gradual ramp-up time, preventing sudden inrush currents that could trigger protection circuits or cause voltage sags, which can destabilize the converter. The layout of your printed circuit board is equally important. A proper layout minimizes parasitic inductances and capacitances that can introduce unwanted resonances. Keeping power and control grounds separate and strategically placing components can help reduce noise coupling. Lastly, consider external factors that may affect stability. These include load transients, input voltage fluctuations, temperature changes, electromagnetic interference, and mechanical stress. Using protective measures like power supply filters, heat sinks, shielding, and robust mechanical design can help maintain stable operation. Before implementing any hardware changes, utilize simulation tools to analyze the converter's frequency response and transient behavior. Validating your design with real measurements allows you to make necessary adjustments to compensation and filtering. In renewable energy and power systems applications, addressing these stability solutions ensures reliable power conversion from sources like solar panels or batteries. By systematically addressing control loop design, filtering, component selection, and external factors, you can effectively resolve stability issues in your direct current to direct current converter design.